Okay, anybody have any homework questions you want me to go over? I think all we've done so far for conservation of mechanical energy for problems I've given you is just getting an idea for, is this value going up, this value going down as things move around. So today I'm going to spend the whole time just doing example problems, and at the end of class today we'll have a quiz, and then I'll assign some real conservation of mechanical energy problems. Okay. So the first example this is kind of a simple one. We've done one where a skier or someone on a skateboard starts at the top of the hill and you figure out how fast they're going at the bottom. This same approach can be used for a skier or a skateboarder or whatever at the bottom of a hill with a certain speed. And you have to calculate how fast they'll be going when they get to the top. So let's say this little hill is 2 meters tall. And let's give this person and skateboard a mass of 40 kilograms. And we want to know, first, how fast does this person need to be going? So that when this person reaches the top of the hill, they're going 2 meters per second. And then second, just as kind of a reminder about how all these things fit together, let's calculate how much work. So what's the work done by gravity over this motion? Over this time interval. Well, right now, the only problems we're doing are conservation of mechanical energy. But when you see problems on a test, you need to know how you're going to approach it. And a problem like this can look like something that you would do possibly with the constant acceleration equations. So you have to ask yourself, like, how do I know that this is a conservation of mechanical energy question? And there's really two big hints that'll tell you, okay? The first one is it's a relationship between a location and a speed, okay? That's what it's asking you for. It's saying when the skier, the skateboarder is at this location, what's their speed? Okay, so that's the first hint. And the second hint is, if you think of all the forces acting on the object during that time interval, they have to fit into those four categories that we can work with conservation of mechanical energy. Okay, those four are, who wants to list some off for me? Someone list off the easiest one and then you're done. Then the other suckers have to do the harder ones. What?
What was the question?
What are the four forces that we can deal with conservation of mechanical energy? Okay.
Is it gravity?
Gravity.
Okay, so gravity, it was spring.
Spring.
It was normal forces in sliding and...
Normal forces in sliding and rolling.
And then centrifugal forces in circular...
And centrifugal forces in circular... She took all the chances, sorry. I'll get to you next time. Okay, so yes, perfect. Those are the four. So if you have a problem that has only those four forces, so here are the two, so here are the hints that it's mechanical energy, that we're going to use conservation of mechanical energy. The first one is that it's asking for a relationship between location and speed. And the second one is that all the forces come from this list. Weight, spring forces, normal forces in rolling and sliding, and centripetal forces in circular motion. Okay, so we feel pretty good about this being conservation of mechanical energy. So to use conservation of mechanical energy, we're going to think of two separate instants. I'm going to call instant 1 the instant when this is before he gets to the hill, and instant 2 is going to be when he gets to the top of the hill. And remember, any problem that has gravity in it that you're using conservation of mechanical energy, you have to decide what you're going to call zero height. It doesn't matter what you choose, but you have to be consistent once you choose it. So I'm going to choose my height equals 0 to be at the ground. Okay, so instant 1 is before he gets to the hill. The gravitational potential energy is the mass times 9.81 times the height, which is 0. And so there's 0 gravitational potential energy at the bottom of the hill. There are no springs, so now all we have to worry about is the kinetic energy. The kinetic energy is 1/2 times the mass times the speed squared. Do we know what the speed is at the bottom of the hill? No, that's what we're trying to calculate, so I'm going to just put that in as v squared, and then I can simplify this to 20v squared. Hopefully we'll be able to calculate that v at the end. And then at instant 2, the gravitational potential energy is 40 times 9.81 times the height. What's the height at instant 2?
2.
2, yep. So this comes out to be 784.8 joules. And now the kinetic energy, this is 1/2 times the mass times the speed squared. What's the speed at the top of the hill? Two meters per second. So times 2 squared. And so this is 20 times 4, so 80 joules. And now we'll add up all the stuff at instant 1, set it equal to the sum of all the stuff at instant 2. So we have 0 plus 20v squared is equal to 784.8 plus 80. And so 20v squared is equal to 864.8. Divide both sides by 20. V squared is equal to 43.24. take the square root. And since we're looking for a speed, we want the positive answer that you get from the square root. And you get 6.58 meters per second. Any questions about that? Okay, so in order to be going 2 meters per second at the top of the hill, the person has to be going 6.58 meters per second at the bottom, like 14 miles an hour or something, pretty fast. Now, what about the work that's done by gravity over this motion? How are we going to calculate the work? We've done two different ways to calculate the work. One is if the force is constant over the motion, and if we know the displacement. We don't really know the displacement here. The easier way to do this is to remember that when you have conservative forces, forces that have potential energy, like gravity or springs, the work is equal to the negative change in potential energy. Okay? So the work is just going to be equal to negative later potential energy, which is 784.8, minus the earlier potential energy, which is 0. And so the work done by gravity is negative 784.8 joules. I said there are two forces acting on this skateboarder through this whole motion, right? There's the weight force and the normal force. Does the normal force do any work? Yeah, that's the reason we can do, so normal force and the centripetal force in circular motion, we can use those because they don't do any work. So even though they're non-conservative and we don't have potential energy functions for them, they do 0 work, which means that the weight is the only thing that does work. Okay? So now think about the meaning of work. Work is a change in energy. And so if you have negative work done, you expect the speed to go down, the energy to go down. Over this motion, does the speed go down? We started at 6.58, we ended at 2, so energy is decreased. And so it makes sense to us that the only work that's done is negative. Anybody have any questions about that? Okay, let's do one with a spring force. So let's say we have this cart. Hold on. Okay. I think this is about to crash. Thank you. Let's say the spring constant is 400 newtons per meter. That's the spring stiffness. And let's say, starting at the spring's resting length, we pull the cart to the left 2 centimeters, so 0.02 meters. And then if we release the cart from that location. What's the speed of the cart when the spring reaches its resting length? Okay, so this is our part A. And then second, during that motion, we want to calculate the work done by the spring. Okay, so imagine pulling this cart, stretching the spring this way and then letting it go. Does anyone have a feeling for what would happen with this, like what kind of motion would happen?
Probably shoot back, right?
It would shoot back, and then if you let it shoot back far enough, so it would pass its resting length, then it would go a little past that because it takes a while for the spring to slow it down. Then it would stop over here eventually, and then it would oscillate back and forth. And if there was no friction anywhere, it would do that forever. Okay. And so what we're asking is that spring is going to go past its resting length as it each direction. And the question is, when it passes its resting length, how fast is this thing moving? Okay, so first we have to think, is conservation of mechanical energy a good approach for this? One sort of short circuit of all of this that's helpful is anytime you see a spring in a problem, remember we haven't talked about any other calculations involving springs, so you know that that has to be conservation of mechanical energy. Okay, but we can also think, okay, it's coming up with a relationship between a location and a speed. And at any instant, the only forces on this cart are the spring force and the normal force as it rolls. And so it meets the criteria. Okay. So I'm going to think of instant 1 as when the spring is pulled 2 centimeters back. And instant 2 is going to be when the spring reaches its resting length. Well, I said the only forces are a spring force and a normal force. There's also gravity acting. Gravity is always acting on stuff. In this case, it's not going to affect the math of the problem. We'll see why. But there is gravity, so let's think about the gravitational potential energy too. Why not? And I'm going to call my height equals 0 the height that it stays at the whole time. Okay. So the gravitational potential energy at instant 1 is the mass times 9.81 times the height, which is 0. So this whole thing equals 0. Now the spring potential energy is 1/2 times the spring stiffness times the square of how far the spring is stretched or compressed from its resting length. So that's 0.02 squared. And if you calculate that, you get 1.28 joules And then the kinetic energy at the instant when it's pulled back is 1/2 times the mass. The mass is 2 times v squared. So I'll just write that as, 1/2 times 2 cancels to 1. So this is just equal to, oh, I'm sorry. That's wrong. What do we know about the speed of this thing when we pull it all the way back before we let go of it? So if you pull something back, hold it there, you're about to let go, what's its velocity before you let go? 0. So we're going to put 0 in there for the speed. And now we'll go to instant 2, where the spring is at its resting length. The gravitational potential energy is 0 again because the height is 0. The spring potential energy is 1/2 times 400 times the distance the spring is from its resting length. What's that at this instant? So this is when the spring passes its resting length. So if x is how far you are from the resting length, this is equal to 0.
Is that 0.02? No, that's the last one.
Yeah, 0.02 was when we pulled it back. Then we let go of it, and now we're doing a calculation for what's happening when it returns to its resting length, when it passes that length. Okay? So we put a 0 in there, and then the kinetic energy, we're trying to calculate this speed. So it's 1/2 times the mass times v squared, and this just comes out to be v squared. So now we can add these up. One thing about the gravitational potential energy, where I had the height equal to 0, that came out to be 0 at both spots. But even if I had chosen my height to be somewhere else, the fact that the height is the same in both of these means we just add on the same amount to both sides of this equation. And so they'll cancel no matter what. So any problem where the height of the object doesn't change, where it stays moving horizontal, gravitational potential energy won't come into the problem. Okay, so let's see, what do we have? 1.28 is equal to v squared. And so v is equal to the square root of 1.28. We want the positive 1, so that is 1.13 meters per second. And I want you to notice that there's no like certain amount of time implied with conservation of mechanical energy. So if this thing, so it's sitting here, right? And you pull this back to here and then release it. It's going to follow a motion like this. Okay? And every time, no matter which direction it's going, that the spring passes its resting length, its speed is going to be 1.13 meters per second. So that's true going this way the first time, and then it's true going back the second time, this way the third time, and that always tells you what the speed is supposed to be. I mean, it's assuming there's no friction, so it'll get less accurate over time, but okay, so the second part now. we want to calculate how much work is done by the spring as it goes from being stretched 2 centimeters to its resting length. So just thinking about what the spring is doing to it, it starts at rest, right? That second point, it has a speed of 1.13 meters per second. So is it speeding up or slowing down? It starts at rest and ends at something. So speeding up or slowing down? Speeding up. And so is that increasing or decreasing energy? Increasing energy. So we expect the work to be positive. Okay, so now let's calculate the work. That's equal to the negative change in potential energy. So that's negative of the spring potential energy at the second instant minus the spring potential energy at the first instant. And so the work is equal to positive 1.28 joules. Okay? In these kind of problems, I always just give you the spring constant. That's just something I provide. But I wanted to just show you how that would be calculated. So here's a question. How could that spring stiffness, K, have been calculated? Well, the way you do it is you hang a known mass from the spring. So let's say, might as well use this same mass. Imagine using this same 2 kilogram cart. Okay, and you measure how much that mass, that hanging mass, makes the spring stretch. Okay. So now you measure how much the spring is stretched. And I'll call that X, okay? Now once you have that, your spring constant is equal to the weight of the thing that's hanging divided by your X. So in this case, we have 19.62 divided by, in this case, the X would have had to be 0.0495. That's what this is. And if you do that division, you get 400 newtons per meter, which was what I gave you in the problem. And you can probably imagine if you have a very flexible spring, this a spring that's not very stiff, this 2 kilogram mass hanging from it will make it stretch a lot, and your X will be bigger. So that'll give you a smaller spring stiffness. If you have a very stiff spring, it won't stretch very much. And so you'll have a smaller X value, and that'll give you a bigger spring stiffness. So that's how it works. Any questions about that? Okay, so now I'm going to give you do a couple of problems where we combine conservation of linear momentum with conservation of mechanical energy. So now we're going to combine conservation of linear momentum with conservation of mechanical energy. Well, what kind of problems do we use conservation of linear momentum for? Collisions, exactly. So anytime you have a problem, so any problem where you're going to combine both of these things is going to have a part that's where it's helpful to use conservation of mechanical energy, and you can go through all those checks, and a part that's a collision. Okay, so here's the first one I'm going to do. Let's imagine that we have this rolling cart rolling along able to roll along a flat surface. And let's say that this has a mass of 0.2 kilograms. And then we have this second cart that's initially at rest. Let's say this is 0.1 kilograms. And we're going to make these two things collide. And when they collide, they're going to latch together. So it's an inelastic collision, the kind that we can do. And the way we're going to make the 0.2 kilogram cart move is, think of like the start of a pinball game when you pull the spring back to launch the ball. So let's say we're going to pull this spring back and then release it and let this go. Okay, so let's say that this spring constant is 600 newtons per meter. That's the spring stiffness. And let's say we pull the spring back why am I using that same value again? Pull the spring back, let's say 0.06 meters. So pull it back 6 centimeters and release it. And we want to know what's the velocity of the pair of carts after they latch. Okay, well, so for stuff like this, you can see we have a spring, so we know we're going to use conservation of mechanical energy to figure out something about the motion of the 0.2 kilogram cart. You can see that they're going to collide and latch together, so we're going to use conservation of linear momentum for that part. So the first part, the conservation of mechanical energy, we're just going to, our instant one is going to be when this spring is pulled back. Our instant two is going to be when the spring reaches its resting length, and that pushes the cart away from it. By the way, what's really going to happen there is that spring is going to speed up until it reaches its resting length. At that point, the spring is going to start to slow down, and that's why the cart will move away from it at that point. Okay, so our instant one is going to be when the spring is pulled back 6 centimeters. Our instant two is going to be when the spring is at 0, is at its resting length. Do we have to worry about gravitational potential energy in this problem? Erasing everything about what I want. Is gravitational potential energy going to affect this problem? No, because the height stays the same for the whole thing, which means that it'll just cancel out. So in this case, I'm going to just leave out, well, I'll put it in here. So gravitational potential energy is 0 at both. So that's not going to affect the problems. So what about the spring potential energy at instant 1? That's 1/2 times the spring stiffness of 600 times an x value, how far the spring is from its resting length, of 0.06, and we square that. And so we get a spring potential energy of 1.08 joules. And then the kinetic energy, again, we're just pulling it back and releasing it from rest. So the kinetic energy at instant 1 is 1/2 times the mass times a speed of 0 squared. So this is just equal to 0. Okay, what about, now we're calculating the spring potential energy when the spring is at its resting length. So that's 1/2 times the stiffness times x squared. What's x when the spring is at its resting length?
0.
0, yep. So this comes out to be 0. And we're trying to calculate the speed. So our kinetic energy is going to be 1/2 times 0.2 times v squared. Or if we simplify it, this is 0.1 v squared. So conservation of mechanical energy says 1.08 plus 0 is equal to 0.1 v squared. Multiply both sides by 10, and you get that v squared is equal to 10.80. Take the square root of both sides, and you get that v is equal to positive 3.29 meters per second. Okay, so what have we calculated now? Let's sort of think carefully about where we are in the steps. What is this speed? I mean, is that the speed of the two of them together? The speed of one of them? What's going on there? Not yet, because we haven't dealt with the collision yet, okay? So all we've done so far is figure out the speed of the 0.2 kilogram cart when it leaves the spring, okay? Now that's the speed that we're going to use to start our conservation of linear momentum problem. Yes? Yeah, exactly. So I tried to draw it like this is just like a little bumper, you know? So they're not attached. So we're gonna stretch the spring back, you know, with a lever like in pinball or whatever, and put this back against the spring, and then let it go. When the spring gets to its resting length, then it'll start to slow down, and that'll just send this 0.2 kilogram cart on its way. So yeah, let's go. All right, so now we're going to do the collision, and we figured out the speed. So this is the speed of the 0.2 kilogram cart after it leaves the spring. And so now we're going to do the collision. And this is going to be conservation of linear momentum. Is the 0.2 kilogram cart, once it leaves the spring, moving to the left or the right? To the right. Remember, conservation of linear momentum is different than energy because we have to put stuff into vectors. So the linear momentum of the 0.2 kilogram cart is the mass times its vector, its velocity vector, which is 3.290. So that's the linear momentum of the 0.2 kilogram cart before the collision. The momentum of the 0.1 kilogram cart before the collision is 0.1 times 0, 0, because it's at rest. After the collision, you can think of them as a single object because they're stuck together. So they have a mass of 0.3. They're still going to be moving towards the right. They're going to be moving along the x-axis one direction or the other. We'd be surprised if it wasn't to the right. But I'm just going to put this in as V0, and we'll calculate that V. It could come out negative, and then we'd be surprised. And so the x equation says um, 0.657 plus 0 is equal to 0.3 V. And so V is equal to 2.19 meters per second. So after you release this spring, the two things will collide, and after they've collided and latched together, they'll be moving to the right at 2.19 meters per second. Any questions about that? So the key thing is that you only use the conservation of linear momentum for the collision part, okay? The rest of the problem is going to be conservation of mechanical energy. Let me do another one sort of like that, but this one we're sort of going to think about it in reverse, the reverse order. So long before there was high-speed video, people were capable of calculating the muzzle speed of bullets shot out of guns. That was something that they needed to know for, people wanted to know the muzzle velocity of bullets that were going to come out of guns and cannons and any kind of projectile. So how do you, now it's pretty easy. I mean, now there's this super high-speed video. You can actually watch the motion of a bullet and divide by the time and approximate the speed. But this is how it used to be done before there was any of that. So this is actually something that, was really a useful calculation in the old days. So let's say that we have a mass, and I'm going to say that this mass is 1 kilogram. And say we fire a bullet into it, and we'll say that the bullet has a mass of 0.005 kilograms. Okay. Depending on how fast this bullet is going, once this bullet sticks inside that mass, this combination of the mass and the bullet is going to swing up some height. Okay, so it's going to follow a circular path up this way and end some amount higher than it was before. Okay? And so if you measure the change in heights here, and let's say that when we measure that, we get a height change of 0.4 meters. You can use conservation of mechanical energy and conservation of linear momentum to calculate how fast this bullet was going at the start. Okay, so what are we going to use? So the question is, what was the bullet's velocity or speed before it's stuck in this mass? So we're going to break it up into these two things. So first is just going to be the collision that goes, so the conservation of linear momentum part is just going to go from the bullet right before it hits this to when it's stuck inside this and this is just starting to spin. Okay? And then the conservation of mechanical energy part is going to be the two things stuck together swinging from this to this. Okay? And because we're looking for this first speed here, I'm going to do it in reverse order. I'm first going to use this height to figure out how fast the combination of things was going right after the bullet stuck in it. And then I'm going to use how fast the combined thing was swinging right when the bullet stuck in to figure out what the speed of the bullet was at the start. Why can we use conservation of mechanical energy here for the swing part? Remember, we need four, like all of the forces have to fit into this category of four things. Well, we have weight. And the only other force on this is the cable pulling on the, well, notice that this mass is going to swing in a circular motion. And so that cable force is a centripetal force in circular motion, which is one of those categories of forces that we can deal with. In other words, that string, that cable force is not going to do any work. Okay? So first, I'm going to do conservation of mechanical energy. For, I'll call it the swing phase. And so my instant one is going to be right after the bullet is stuck in the mass. So this is instant one. And instant two is when the mass and the bullet get up to their highest point. Okay? We have to choose a height equals 0. I guess I'm going to choose that to be where the mass and the bullet are at the start of this motion. So the gravitational potential energy is equal to the mass. What's the mass of the thing that's doing this swing? What?
Didn't you say 1 feet?
So notice that this is the two of them swinging together. So it's going to be the sum of those two masses. So 1.005 times 9.81 times at instant 1, what's the height of the combination of masses? 0, yep. And so the gravitational potential energy there is 0. then the kinetic energy, so this is going to depend on the speed of the mass and the bullet together right after the bullet sticks into the mass. So that's going to be 1/2 times that combined mass, 1.005, times the speed that we don't know squared, and we're going to calculate that. So this capital V is going to be the speed of the combined thing just after the bullet is stuck inside. And so I'll just write this as 0.5025 V squared. Now instant 2 is when it swings up to its highest point. So the gravitational potential energy is 1.005 times 9.81. What's the height at instant 2?
0.4.
Yep, exactly, 0.4. And so we get a value of 3.943 joules. And now the kinetic energy at instant 2, that's equal to 1/2 times 1.005 times the speed squared. What's the speed of this combination of things when it gets to the highest point, right before it starts to swing back down? 0, yep. So 0 squared, and so the kinetic energy is 0. And so now conservation of mechanical energy says 0.5025 V squared is equal to 3.943. So V squared is equal to 7.848. Take the square root and you get that V is equal to positive 2.801 meters per second. So now what we figured out is the speed of the combined mass right after the bullet sticks. Okay, well, now we're going to deal with the collision. And for the collision, conservation of linear momentum, we need vectors for the velocities. So we have a speed here. What direction is this thing moving the instant after the bullet sticks in there? What? Yes, perfect. So notice that this is a circular motion, a part of a circular motion. So right here, the velocity is this way, just exactly to the right. Okay, and so conservation of linear momentum. So now we're doing the collision. The mass of the bullet times its velocity to the right that we don't know, plus the mass of the hanging thing times its velocity vector before the collision. That's just 0, 0. It's just hanging there. Is equal to the combined mass times the velocity of the combined mass right after the collision. And that's 2.801 in the positive x direction and 0 in the y direction. So the x equation here says 0.005 little v is equal to 1.005 times 2.801 So 0.005 V is equal to 2.815. Divide both sides by 0.005 and you get that V is equal to 563.0 meters per second. And that's in the positive direction, so it's going this way. So by measuring the height that this thing swings up to, you know, and that's pretty easy to measure just by eyeballing it, we're able to calculate the speed of the bullet when it hits the mass. This thing is called a ballistic pendulum. Any questions about that? Okay, well, that's all for today. I'll give you some problems to work on.